we shall make a detour from our journey into the Pascal triangle. So a detour is like a side trip instead of going straight to our destination. And by the way, our destination here is the binomial theorem. The proof to the binomial theorem. That is our ultimate destination. And we shall temporarily make a side trip to the combination formula. You will know the significance of the combination formula in the next video, not in this video. You may still recall the combination formula because it is a counting formula. What is a combination? A combination is a selection of elements from a set so that the order of listing the selection does not matter. So let's say, for example, I have this set. It contains 3 elements, and let us produce one combination of 3 elements and list all combinations of 2 elements. Okay, so how do we do it? How many combination of 3 elements can we form from A, B, C? Well, there's only one combination. It's A, B, and C. Okay, so in combination, we don't pay attention to the order with which the elements are listed. A, B, C is just the same as CBA or BAC. How about this? List all combinations of 2 elements from this set. So what are those? Well, it can be AB, it can be AC, and it can be BC. These are the only combinations of 2 elements that can be chosen from a set containing 3 elements. Well, maybe you can still recall the combination formula. And you know what? Our concern really with the combination is not what those combinations are. No. Going back to your maybe grade 9, grade 10, these were introduced to you. Our interest is in counting how many combinations there are of R objects from a set containing n elements. And I hope you can still recall this. Because for people who were not paying attention to their math subject, this is a big thing. This is entirely a new notation. But then again, I hope you are the kind of student who had been at least somehow paying attention to your lessons in math. So how do you read this? This is read as n taken R. Okay, so it's like you have a set, okay, containing n elements, and then you will choose R number of objects from that set. And this formula will tell you how many combinations of R objects can be taken from the set with n elements. That is quite a mouthful of sentence to say. There are many notations for this formula. Okay, so we call this the combination formula, n taken R. That's how you say it. But we have other notations for this. This is also n taken R or n combination R. I think your calculators have this as a symbol for the combination formula. So what is our interpretation of n factorial? Okay, so that is how you read it. N factorial is 1 times 2 times 3 times 4. Although, okay, so other teachers and other writers prefer to write it in this way. So it's the same. 4 factorial is equal to 1 times 2 times 3 times 4, or equal to 4 times 3 times 2 times 1. Okay, so let us go to the earlier examples. We have a set containing 3 elements. How many combinations of 3 objects can be taken from this set? So we will apply this formula. So it's going to be 3 factorial is equal to 3 minus 3, that's 0. Look at that. So look at this. This came from 3 minus 3 factorial divided by 3 factorial and 0 factorial. Okay, so just in case you forgot this, This is actually one of your properties of factorial. It's part of the definition of the factorial notation. 0 factorial is equal to 1. How about this one? How about picking a combination of 2 objects from a set containing 3 elements? There are only 3 combinations of 2 objects taken from this set, and applying your formula, this is how it's going to be. So what's that? That's 3 factorial. And then this one is 3 minus 2. So that's 1 factorial divided by 2 factorial. There are many computational exercises concerned with combination. So sometimes, to see that the 2 factorial gets cancelled, sometimes this is how you can write 3 factorial. It's 3 times 2 times 1. But times 2 times 1 is just the same as 2 factorial. Okay, and then okay, so let us do some exercises. What is 4 taken 2? Okay, it's 4 factorial over 4 minus 2. Okay, so that one came from 4 minus 2 factorial. And again, look at this. 4 factorial is equal to that. 4 times 3 times 2 times 1. But 2 times 1, that is just 2 factorial. And look at the numbers that gets cancelled. 2 factorial divided by 2 factorial is 1. 2 factorial is just 2. And this one has 2 for a factor. So what is left here is simply 2. And so 2 times 3 is equal to 6. How about 4 taken 3? So again, this one is, it came from 4, okay, minus 3 factorial. Okay, so that's just 1 factorial. And then, look at that, 4 factorial, which is equal to 4 times 3 times 2 times 1. But that is just equal to 4, okay? And then times, look at that, this is 3 factorial times 3 factorial. Okay, so why did we write it that way? Because it's easy to show to students who are new into these notations, to these symbols, that 3 factorial and 3 factorial gets cancelled. And what you have is 4. We go to the next one, 7 taken 5. Okay, so this is going to be 7 factorial over, okay, where did this come from? This came from, you don't ever distribute the exclamation point to 7 and 5 like applying the distributive property of multiplication over addition. You don't do it with factorial. So that's 2 factorial. 7 factorial again, look at this, 7 factorial, that is just the same as 7 times 6 times 5 times 4 times 3 times 2 times 1. But look at that, that is just 5 factorial. Okay, and by writing it that way, you can see that 5 factorial divided by 5 factorial is 1. And then what happens here? This is 2 times 1, and 6 is 3 times 2. So 2 gets cancelled. And what is left here is 7 times 3, and 7 times 3 is 21.